Welcome. We're going to look at the decomposition of potassium chlorate and practice our use of stoichiometry in chemistry. I'm Miss Mixell, and I'm one of the chemistry teachers at Eagle Crest, and I hope this is helpful. So to get us started, let's start by talking about what you know about potassium chlorate. Can you take a second and write a valid formula for me? Awesome. Hopefully you checked charges and found that potassium has a +1 and chlorate a -1, so it would come together as KClO3. All right, if potassium metal is excited from the energy of the reaction, what color would you expect to see? Hint, you might want to take a second and Google what color metals make in flame tests. I bet you found that potassium makes a very pretty light lavender color when heated in a flame test. So that's the color we would expect to see in this reaction if the metal is excited by the energy of the reaction. All right, let's take a second and watch a demonstration of the activity that we're going to embark on.
So at the moment, I'm heating it up so that it can melt. And when we've got molten potassium chlorate, we'll almost be ready to do this decomposition reaction. So the potassium chlorate has now melted. We have molten potassium chlorate. There's a lot of thermal energy there, but it's still not going to decompose as quickly as I would like, even though temperature is one of the major factors for increasing the rate of a chemical reaction. We need to provide a little bit more energy, and I'm going to use Skittles. You could also use gummy bears. That's the traditional way of doing this experiment. But the main component of candy is sugar, C12H22O11. It's a hydrocarbon. When I put a Skittle inside there, it's going to combust. It's going to burn. And that bit of energy is going to initiate the decomposition reaction for the potassium chlorate.
All right, that was a pretty awesome decomposition reaction, wasn't it? Let's take a second and write the decomposition reaction for potassium chlorate. Make sure to show your products with states of matter. You might have struggled to write this decomposition reaction. It's not easy to figure out what the products will be because potassium chlorate could break apart in a variety of ways. And so, what we're going to need to do is experimentally figure out what our products are, since we won't be able to just automatically say set products form. You might have written a decomposition reaction that shows it's going to break apart into potassium chlorite, ITE, along with oxygen gas. Or perhaps you predicted that it was going to break apart into potassium hypochlorite and oxygen gas. Or maybe you said it was going to break apart into potassium chloride and oxygen gas. Or another possibility is people might have said it's going to break apart into solid potassium and produce both chlorine and oxygen gas. How will we know which of these four possible reactions occurred? To do this, we're going to need to use stoichiometry. So, our essential question for today is how can we experimentally determine the products that will form when potassium chlorite decomposes? And we'll do this using stoichiometry. We can decompose a set amount of the solid potassium chlorite, and then we'll be able to measure the product of the reaction to determine. Take a second to balance all of the reactions, because to be able to use stoichiometry, we're going to need balanced chemical reactions. Okay, hopefully you found that 2 moles of solid potassium chlorate will decompose into 2 moles of solid potassium chlorite and 1 mole of oxygen gas. Or you might have found that there was a 1 to 1 to 1 mole ratio between the decomposition of solid potassium chlorate, which will produce 1 mole of solid potassium hypochlorite and 1 mole of oxygen gas, or 2 moles of solid potassium chlorite decompose into 2 moles of solid potassium chloride and 3 moles of oxygen gas. And finally, our last balanced reaction would be 2 moles of potassium chlorate decompose into 2 moles of solid potassium, 1 mole of chlorine gas, and 3 moles of oxygen gas. If we look, which product will we be able to isolate and measure? In each of our 4 possible reactions, what would be the easiest product for us to isolate and measure? Hopefully you told me that isolating and measuring the solid product, whether that's potassium chlorite, hypochlorite, chloride, or just solid potassium, would be what we should isolate and measure. So we are going to run this experiment. We're going to do it a little bit differently than what we saw in the demo, because instead of using Skittles as a catalyst, we're going to use manganese dioxide. Manganese dioxide will act as the catalyst to get the reaction started and the decomposition to occur, but it's not going to actually undergo a chemical reaction itself. There'll be no permanent chemical change. So its presence in the test tube will be the same both before and after the reaction, and thus we can ignore the mass of our catalyst as we do the mass of the reactants and the mass of the products. So our procedure today will be to place 0.7 grams of manganese dioxide catalyst into a clean, dry test tube, heat it for about 3 to 4 minutes to drive off any moisture. Then we'll cool the test tube and place it in a small beaker so that we can mass it. This will represent the mass of the empty container, as throughout the experiment, the mass of the beaker, the test tube, and the manganese dioxide catalyst will not change after the reaction. All right, once we have that measurement, we'll add approximately 1.5 grams of potassium chlorite, our reactant, to the test tube. We do need to make sure that the solid is transferred to the bottom of the tube and not sticking to the tube walls. We'll record that mass of empty container and reactant. Then we'll mix the contents using a glass stirring rod until we have a uniform gray color. Let's be sure not to lose any of the reactant as we remove the stirring rod. So please note, for the purpose of our calculations today, the mass of the beaker, the test tube, and the manganese dioxide catalyst can be subtracted out from the mass of the solid product, since manganese dioxide will not react. It's a catalyst. Its presence speeds up the rate of the reaction, but it does not actually react or undergo any permanent changes. All right, step 5 is to heat the test tube gently at first until we notice the test tube appears to boil. This is the first sign of a rapid release of gas. As the release of gas slows, we'll begin to heat the test tube more strongly, but we need to move it back and forth along the heating zone. We want to continue to heat the tube for about 5 minutes, cool it, and weigh it in the beaker. And then we'll repeat this heating, cooling, and weighing cycle, in other words, step number 6, until we have a constant mass reached. 2 successive weighings should have a mass within 5 thousandths of a gram of each other, or a constant mass is reached with 2 successive weighings. Let's get our experimental data. Okay. Using the video, you should have been able to record the mass of your empty container, as well as the mass of the container and reactant, and the mass of the container and the product. From that, you should be able to calculate your mass of your reactant and the mass of the solid product that was produced after the reaction. Now we'll need to use stoichiometry to compare our experimental data to our theoretical calculations. Using stoichiometry, calculate the theoretical mass of solid product that should form based on the amount of potassium chlorate that was decomposed in the experiment. We'll need to do our stoichiometry 4 times, once for each possible reaction, so that we can determine which reaction actually occurred using our experimental data. For each of your stoichiometry problems, you'll start with the mass of the potassium chlorate that was decomposed, and you'll be solving for the mass of the solid product based on your balanced reaction. Use your stoichiometry to make a claim answering the essential question. That's it. I hope you do a great job. Thanks for watching, Raptors.